All right, so someone had a question in general. Again, we're talking about different things that we need to study. So when we're talking about IMFs, all right, we're talking about this attractive force, and we'll get more specific in a second. So if you're like, I'm not sure what to write down right now, it's fine. But two things that a lot of people do have issues with over the years, I've seen it, and it's a real thing. I don't understand the differences between like melting point and boiling point. I think the biggest thing for me when I first learned it, I didn't understand why they both are up when it's stronger IMFs and they're both down when they're weaker IMFs. Like, shouldn't the melting point be higher with a strong IMF and lower for a strong IMF? Like higher for one, lower for the other. And I guess this is what you want to think about is a freezing point. I think the melting point, I hope makes sense, is that if this is a really strong force in between, I got to put in a lot of energy before it breaks apart. If it's really weak, it doesn't take a lot for it just to break apart, so the melting point would be really low. It can start boiling right away, like an alcohol is really low compared to water. Yeah, Kevin.
Is melting point and boiling point the same?
Yes. No.
No. You just went over what it wasn't.
No, sorry, I meant to say boiling point though.
Get off my... What do you guys say?
Case.
Oh. Yeah, get off my case.
Thank you, Kevin.
You're welcome.
All right, so good correction. So boiling point, I'm overcoming, I'm going from a liquid to a gas and it breaks apart. That's why, for example, let's talk about these two. If I would have this versus this, okay? So if I'm talking about boiling points, here's the first one. And I asked you on the test, which one has the higher boiling point? That's what a lot of the test is going to be, this or that, this or that. Give me 2 sentences or so. One sentence should be declaring which IMFs are in which, and then just reinforcing that it's the stronger or the weaker IMF in that situation. And that's why you chose it. So do not assume because of H bonding, then you're done. You need to at least say that that is stronger than the other ones if you're talking about 2 things or more. So when I look at this, here's the tricky part in this one. What do they have? They're both H bonding, but if you draw it out, sometimes it matters. Right, and these are H's. Which one? And you've actually done this in lab when we were doing esters and things like that. We didn't have the water bath. The water wasn't boiling, but what happened in a lot of our test tubes? It actually started boiling. Like bubbles, it had a rapid boil. Well, that's an alcohol. So if I look at that, this part's H bonding. But both of these are H bonding. So there's 2 H bonds in that. And what's the rest of this if we had to like classify it? More or less it's what?
London.
More or less it's London forces. LDs. So which one's going to have the higher boiling point? Water or alcohol? H2O. So that means, and if you don't like the term stickiness, that's fine, but the stronger the IMF, the stickier these are together, and it's more, it takes more energy to break them apart. These are more attracted to each other, so I gotta get, more and more energy before they break apart. All right? But, what about freezing points? So let's just do a different one. I want lower freezing point. I'll make 2 of them up. Now, if you're like, I don't understand, like, what are you talking about? It's when I say NH3, it's a whole slew of NH3s. When I say C3H8, it's a bunch of C3H8s that are attracted to each other. All right. So again, get on the test, and I'm going to ask you to classify these. All right, so what is what? What's the propane? That's a London. Right. That's an LD. And if you're at a point sometimes, like on the 14-minute video that I made for you guys, I had to draw them out one time for you. Like, be like, you know what, sometimes you have to draw it out. So if you're ever unsure, you might have to draw it out. Like, okay, fine, I gotta look at this. Oh yeah, it's symmetrical. Like maybe you just go that far. Maybe. Then NH3, is that polar or non-polar? Like, you gotta get to that sometimes. I didn't mean to, dang it, I didn't mean it to be N. I'm going to cheat. Still going to give you the same answer, but the only reason why I'm doing that is I wanted something different. It gives me the same structure. The reason why I'm just bringing this up is that those lone pairs are really important. Those are polar. So those would be dipole, dipole. Why did I change it from N? Why did I take out the N?
So did H
Yeah, H bond. I just wanted something different. Still going to be the same idea though. So which one's a stronger IMF? You got to process through it. This one's the stronger IMF. This is the weaker one. Your job is to figure out what you're looking for. So Molly's question, I explain a little more at freezing point. What has to happen is freezing point, you are going from a liquid to a solid, right? So you're going from more energy to less energy. And why is that important? If you ever get stuck, you do want to go back to the atomic roots of it all. I have to slow these, so these are all moving around. They're liquid, so actually they're kind of just moving around like this. I have to slow it down enough so all of a sudden it gets locked in, and the attractive force between these two are stronger than the kinetic energy that is in the atoms. So if it's a stronger IMF, you don't have to slow it down as much, because eventually they're just going to, like if they're really strong, they're just traveling, whoop, they'll connect, right? But if they're really weak, I could drive right by and nothing's going to happen. I got to slow down. Oh, okay. Now there's a greater, the force between them, the IMF, is greater than the force that is resulting from the kinetic energy. I don't know if that makes sense. Like I got to slow it down so much to get them to be attracted to each other. So it's, again, think of stickiness. If they're really sticky, you're going to go right by, boom. Oh, I can't even stop myself. There we go. If they're not sticky at all, they're just going to keep going by, and you got to really slow it down. It's like a Post-it note. It's like you got to really be careful. Maybe it'll stick to your paper. So that's the difference. So I'm looking for the stronger or weaker IMF. The weaker IMF. That one. It's important. I mean, once you get this straight, it's going to be good. And you're like, well, this is all we had to do yet. I'm really getting confused. I know. There's a lot of things that we have to talk about, but you got to keep a few things straight. To me, this is what I try to remember. Vapor pressure and volatility are the only ones that are opposite to the strength of the IMF. So if I want a higher volatility or a stronger vapor pressure, those are weaker IMFs. Everything else, I want stronger, stronger. I want lower, lower. I mean, that's one way to also have it down, but obviously we want meaning behind it. It's not about just memorizing it. So, questions and concerns on that? We're going to draw a phase diagram. Jeff Bray.
Say we have two hydrogen on H bonding.
We have two hydrogen, say H bonding.
Okay, well, we have two H bonding.
Oh, you said say.
Okay. One
Okay.
HF and one is OH. Which one would be stronger in that case?
You gotta have to repeat that. I'm sorry, I wasn't.
One is HF and one is OH. Which one would be stronger? We had like a question like that on the review.
Yep. Great question. HF or OH? It comes down to electronegativity. So technically HF is a stronger dipole than OH. Here's the thing. On one of the review or the notes today though, it was this actually. I'm going to give away a part of the lecture. And I totally botched this problem because I wrote down some things incorrectly. If you look at this, let me just redraw them this way. Although this dipole is stronger than this dipole, there are two of them. And that's usually what you're going to see. So Jeffrey, almost every time whenever there's O, it bonds twice. When there's F, there's one. And N usually bonds 3 times. Because that's just the way it works. N has 3 lone pairs, or 3 lone electrons. O has 2. Fluorine only has 1. So this actually is going to be the strongest. That's about the only situation you're going to have to kind of come into. My job's not to try to trick you. It's pretty clear the situations that I'm trying to pose to you.
Can you go over why a strong IMF would mean a low vapor pressure?
Yes, let's do that. That's a great question. All right, so let's review this. This you want to know, because vapor pressure will show up on the test. And I think if I had to pinpoint one thing that students mess up the most, vapor pressure. It is. So what happens is you have this pressure, it's always coming off, and then this is always constant in your situation. There's atmospheric pressure, and then there's vapor pressure. Okay? So, you got these molecules. I'm going to call it XY. And they're attracted to each other. Where do they leave? Where do they exit in this beaker? Because it's going to be important where we go in the future here. Where are they leaving from the beaker? On the surface. Nothing's ever evaporated from the bottom. They're not digging a hole out of prison from that way. Like, they got to be up here so they can leave. So what happens is sometimes molecules just get enough, like they bump into each other, boop, and all of a sudden they get to leave. Another one slow down, oh shoot, and they fall back into solution. That's what that whole evaporation condensation situation is. And the reason why we know that, it's like I don't put water on the table and tomorrow it's gone. Be like, oh my gosh, during the night they must have boiled the water on my table and that's why it's gone. Like all those puddles in the street, every night they must boil and the water's gone. No, with wind, I mean, especially as a tennis coach, see it all the time. You get the water thin. Why? Because then there's less molecules on the surface. If there's any wind or sun, all those molecules on the surface keep just leaving until there's nothing left on the top. And that makes you break if we're ready for a match. Well, the thing is with this is that if they're ready to go and they're going to leave, the stronger the IMF, the lower the vapor pressure, and the reason why is, again, think of stickiness. They're not going to exit, so the molecule doesn't easily leave. It's not a technical definition, but I think it works. So just think about it. They're attracted to themselves. So if they're really sticky and they're attracted to themselves, they're not going to exit that easily. Okay. Now, boiling itself, a boiling point is when your vapor pressure is greater than your atmospheric pressure. I need you to be able to understand the difference between that. Again, you're always going to have evaporation, and we proved that through just normal life experiences. Again, you don't see water just boiling on the table, yet it does disappear. And you don't think, wow, I always miss it every time. I never get to see it. Kevin.
I don't understand how if you have a stickier solution, I guess if they're more tightly packed or whatever, then how it would take less pressure or less of the vaporization.
Vapor pressure is how easy or how much the solution, it's also volatile. This means being volatile. It's how ready it is to evaporate. So the greater the push away, the faster that'll evaporate. So that's why we smell certain substances so easily, because it's constantly evaporating. I don't know if that kind of answers your question there. So again, it's the readiness for it to leave, to exit, to evaporate. So a stickier substance, a substance with higher IMS will have a lower vapor pressure because it's not going to evaporate, it's going to stay in liquid phase. Can't remember who asked it, but I hope that's somewhat answering your question. So then, if I ever gave you that information, I'll tell you, sometimes it's maybe it's a two-step problem. So I did this today in class. Let's do this right here. What if I said, you have Q, I'll make this up. Q is more volatile than J. You know that's the only element that is not, only letter that is not on the periodic table? J. Now you know. Now everyone's looking. Oh yeah? Good luck.
Where's Q?
It's there. I think it's in the newer ones. All right.
Sure.
answer these ones, please. So, volatile, you need to have this down. Volatile means to easily evaporate. So first, when you see a statement, there will be some sort of a question on the test where I will make a general statement, like, and it won't be anything you know. Like I will just give a generic compound. Like it's not about that. I've already given you the statement, so it's not your job to figure it out. It has given you a clue of IMFs. So based on this comment, is Q or J a stronger IMF? Rory?
J.
Why?
Because Q has weak IMFs because it has more vapor pressure, so it is more able to jump over the water or the bubbles.
Hey, how are you?
Good, how are you?
Good.
I come this semester.
Nice. Yeah, we're doing a review right now. Doing IMFs.
Oh no. I haven't had that, and I had my whole AP Chem, all my AP Chem stuff with me at school.
Hear that?
Yeah.
All of our AP Chem stuff is cool.
It's hard.
Good.
It's hard.
Hockey game tonight. Hockey game tonight at the Pole Grounds.
Yeah.
Be there. 4 o'clock. Well, 4:30, 3:30 maybe. I don't know.
Yeah.
I don't even know.
Rory, it's 3:24.
I was just gonna get up.
Well, I gotta stick to my word.
I got a game, so.
All right, so once you have that down, then you go to the rest of them. So which one's going to have the lower boiling point?
Q.
Q. And because you just say Q, because it have lower IMFs. Higher vapor pressure? Q. Because the higher the vapor pressure, the lower the IMF. And then higher viscosity means you need a stronger IMF. So that would be a J. Okay? So it might be set up, maybe I just have you give this initially and just give a general theme or a general sentence about it all. So what Rory said actually would more than cover the rest of it because you're declaring the IMFs. But then you'd want to just say, well, lower boiling point, I'd want a weaker IMF, higher vapor pressure, weaker IMF, higher viscosity, a stronger IMF. So that is something that could definitely go down that path. Okay? All right, we are going to try. I'm going to make this all up, and we'll see how we do. It's just a little hard to do this from scratch. We'll try. All right, so you'll want to kind of write with me here. I got to give you a bunch of points. So here we go. All right. Here we go. This is gonna, it's not that easy. All right. So what if you were told these 4 things? All right. Please write that down. What we need to do is if I give this to you, now I might give it to you, I could be really mean and give you all sorts of different pressures. I give you one in torr and one in KPA and one in ATM, and then you got to decide and get them all in there. So do you remember 760 for torr and 101.3?
Is it on the yellow sheet? No.
Actually, it might be.
Oh.
Yeah, you should talk to that test guy.
Talk to the test guy.
See what you can do.
All right, here we go. So, what is important to this is that you need to be able to not necessarily, you don't need to get this to scale. You don't need to do this to scale. You need to make sure that it just looks like they all line up. So for example, I'm going to put one ATM here. So I have ATM. If you do not have a label, you need to put labels on here. I'm gonna put them below just because I don't want to write, I need to put numbers there yet.
Should we have 7?
I'll show you. I had 2 1s, so I wanted to do that first. So, yeah, you could put a 7.2. Now you're like, that's not the scale. I know. Like, I'm not, it's okay. Now, those of you that have done a lot of graph work, what you could do also, I believe it's like you cut it like that, and then it's showing like it's not the scale. Okay. But it's not that big of a deal. It's a general shape that your goal is. So what you're going to do is what you can do is just look at all of them. So the far end, I want 175. Okay, I'm just going to move down. So that's a point right here. So I'm just going to make that one because that's the 7.2 and the 175. I have 1 ATMs at 75 degrees. Again, I know that that's not the scale. I have another one at -20. And I have another one at 0.45. And -15. Again,
Negative 15 go first.
well, now that just ruins what I want to do.
Make it -25.
I just did it again, didn't I?
Yeah, you did.
You should switch the dots. No.
Oh.
This guy.
Fine, leave it the way you have it. You'll have the opposite phase diagram. It's okay. You'll still learn something from
I'm not learning
I've lost like 20.
it. Anywho, then what you do is you take this and you got to understand some things. That this is going to branch off this way. This is going to branch, and it's going to be, if it's to the right of this, it will follow that path. It's already a positive slope. It doesn't matter if it looks like that or if it's straight, but it's not going to hit this line and then balloon back the other way. Okay? If we had it like that last one that I just had, then it would have looked like this. It's not a bad thing to see. It would have looked like this, and then instead, it would have looked like that. Okay? You need to see the 2 different shapes. It's good to see. So when I had the -20 and -15 switched, all I want you to be aware of is I'm just connecting the dots. We're making a Y. We're making like a fork. So is it closed or is it open? The way I know how, if it's closed or open, is if the triple point is to the left of that, which is the freezing point or the melting point. If it's to the right of it, so here's my points on this one. If it's to the right of it, then it's going to shift open, like a open Y versus like a closed Y. And I might ask you to label everything. So today, what we learned about a little bit, although I couldn't show you liquid CO2, which was really frustrating. I have a solid, a liquid, and a gas. No matter what I have, I'm just going to do it over here as well. It's not a bad idea maybe just to draw that on the side, just like, oh, that's the other. Like those are basically your 2 shapes you're going to come up with. I'm not going to take a template and cover up your test, and if it doesn't match mine to the, like, it's like, oh, I see some writing, you lose points. Like, it has to look exactly like mine. As long as it looks like either the first one or the second one, depending on what you're supposed to draw. So what's the key? The blue dots right there, or here the 2 red ones. Like it's where that triple point is versus the freezing melting point. Okay? Then I might ask you some questions like, let's do this. Which one here of my 2 drawings is the solid more dense than the liquid? The left one or the right one? Which one is the solid more dense than the liquid? And we just covered this right at the, well, actually way at the beginning, but you may not remember it. Anybody remember? Yeah, Jeffrey?
If the slope is positive, the solid is more dense.
So left or right? Correct. This one is a positive slope right here. So the solid on this one is more dense than the liquid. Okay? This one, the liquid is more dense than the solid. I like to, in a visual manner, you can see the fact that the solid is looming over the liquid, so it is more dense than that. Now, you could get confused with that and be like, wait a minute, I see that it's above it, so, you know, it's floating above, so you can't get confused by that. Like that will counteract your thinking on that. But a graph can show you this. I'm not going to ask you something and be like, well, are we supposed to know that it's more dense or not? No, the graph will show you if it's more dense or not. Rory, is that a question?
Yeah,
You're 3 minutes late. Go.
At certain points, will the solid be more dense? No.
Well, I mean, this is always more dense.
Yeah.
Well, here you don't even have a liquid, but then once you're starting here, it's always a positive slope on the left one.
How about for, oh, okay.
And here it's always, the liquid's always more dense the entire way.
Okay, gotcha.
Okay? Then, I can ask you some other questions. I could give you a point. Wherever I place that, I could say, you're at 75 degrees and 0.75. Thank you, sir.
So we gotta show us, pause it, no, pause
We
it.
had a hockey.
Then go. Back? Yeah, $75 per share. What if I say this point, I say as it loses temperature, as I reduce the temperature, what phase, or sorry, what process will it go under? So if I say this loses energy, or I reduce the temperature at like 75 degrees and 0.75 ATM, I mean, you would have an idea where that's going to go. Well, what process does that go under? Condensation, right? If I tell you on this, let's do another one. Somehow I say 0.3 and negative 30, and I say I add temperature. I add energy to it. So you find where that is, and you're going to draw an arrow, because these are the kinds of questions I could ask. That's going to undergo sublimation. So those are the follow-up questions after I give you a phase diagram that you would need to understand. And this one for sure. Knowing the density is a must. Okay? So you'd be given all the points that are in blue on top. You have to have those down. Okay? Any other questions on the phase diagram? Yeah, Jeffrey.
What's gas to liquid flow?
Condensation.
No, gas to solid.
Gas to solid deposition.
Yeah.
DEPOSITIO. You need to know that. Yep.
So sublimation was that way?
Sublimation is gas solid to gas. Gas to solid is called deposition. It's probably the only one that you've never heard of before if you haven't heard of one. I mean, if you don't know melting and freezing, then we'll break it all down.
We'll see you after class.
Yeah. We'll see you next year to start over again. What? Yeah, it's just dumb. Is there, we're only going to do a couple more little ones. Is there anything else that someone's like, I wanted to see something like this before, or else I'm just going to make up one or two more quick examples. I'm not going to do cooling or heating curve tonight. We'll do one of those again tomorrow. I'm going to make a pre-made kind of slide tomorrow. I'll be here after school if you need me, but I am in a science meeting all day, unfortunately. So tomorrow is more about working on your stuff, and then there's going to be about a 10 minute YouTube clip of just what's on the test, breaking it all down one last time, just general big ideas. But if you need more help, I'll be here again tomorrow night. But
So we're gonna go over a cooling and heating curve tomorrow, but you're not gonna be there?
I'm going to do one on a video again.
Oh, okay.
I'm going to do one. Yep.
Someone's just gonna try and, they're gonna point at it.
We will go over it. Okay. Let's finish with one last problem. Here, hold on. I kind of had a guide that I was going off of a little bit. Ooh, all right, here we go. All right, here we go. Which one is linked to the correct IMF or attraction? Just how about correct force? Here we go. And there might be more than one. I actually do want to stress IMF, because or else I don't want to do intra. I know it's crazy, but there's only one that has the right bonding IMF to its structure.
Oh gosh.
All the other ones are wrong.
Why you do this?
Rory?
BCl3? No? Oh.
No. Reason why? That would look like that.
Trickster.
It is a.
That's gonna be London.
Is this H bonding? First one. No, just because there's H's doesn't mean it's H bonding. You gotta have fun with it. So that's not right. This isn't right. Okay, and you're like, well, that is covalent because it's not a metal and a non-metal. I totally agree if I was talking about an intramolecular force. But I'm talking about one of these to another one of these. So what is this bond in between them, or that IMF? What are these? Sorry, I did 4 instead of, I did 6 in my picture. Sorry. What are these? London. These are London. They're symmetrical. Hydrocarbon chains that only have hydrocarbons in them, hydrogens and carbons, it's London.
Would there be a double bond in the middle?
Yes, I messed it up.
Okay, gotcha.
Go to hockey. So that's not right. HBr, ionic.
Nobody knows.
Why isn't it ionic?
What's ionic?
That is a great question. Ionic is when you have a positive and negative charge. The problem is an H can confuse you. It has to be a metal and a non-metal. Hydrogen is not a metal. So that is not a ionic charge. Kevin?
Would AlCl3 be an ionic then? If you're oh, you're saying the
Yeah,
whole-
it is, but that's not the strongest bond there because, well,
The overall charge has to be positive or negative? Is that what you're doing or no?
And also, if you have a polyatomic ion too, right?
you could have a polyatomic ion, yes.
Does that make it automatically ionic?
Yes. So it comes down to this. And I guess, to me, I'm coming through a little bit of a monkey wrench. Well, what if it has a metal in there? The issue is with this also, we're not talking about strength, we're talking about what matches up. And ionic and covalent are usually more about internally, like an intramolecular force. If you look back at your notes, intramolecular forces, first off, are the ones in between, within the molecule. And I want to have the IMF force that is between the molecules. So even if you write ionic, it's not an IMF. Covalent's not an IMF. Right? IMFs are H bonding, dipole-dipole, and hydrogen. Okay? Even if I did have network, why isn't this a network? I mean, it would only come up in a very, very specific way. What has to, like, the only thing I'm making you recognize about a network solid, and they're very strong, and I'm just gonna, like, they're stronger than IMFs. That's all you need to know. But what has to be present in a network? And that's about as much as you need to know that I told you. Carbon, silicon, and it's like, that's all that it literally is. That's about what you need to know. The one that you should know about, by the way, that is a little confusing, the only one that I would say you need to, otherwise they'll say like diamond, or graphite, or just carbons, or just silicones. SiO2 is quartz. Now, it may not come up at all, or just if it does, you need to just recognize, I'm going to be very true to the things that we've been working on, the things that we've been reviewing, but this is a repetitive network. But, why is ACl3 the answer? By the way, why that is not network is that because that's an ionic compound anyway. But it is a non-polar. It looks just like the BCl3. Al and B are in the same group, so you have a structure like that. It's totally non-polar, so that one would be considered London. Right? And you just would have to explain. Well, the ACl3 is non-polar, which would have the London forces. In something like this, if it ever did do something, I've used similar problems like this some years. I don't expect all the other explanations. I expect you to explain the one that is correct in something like that. If you're ever unsure, like on the test, you can always come up and be like, how many do I need to explain here? Like, I would tell you, like, well, just explain the one that's correct, not all the ones that are wrong, and something like that.
Would you just explain it by saying it's non-polar?
I would say due to the structure, you could. I mean, if you could land trigonoplanar, that would be huge. But if not, you'd at least say the geometry causes it to be non-polar, which would mean that there's only London forces. Or only LD forces, yeah.
So like, stupid.